Okay, this time we're talking about 13.6 about planes. Okay, first thing, just a reminder that the dot product equaling 0 means that the two vectors that you dotted with each other is orthogonal. And that's going to come into handy with the planes when we're trying to find orthogonal vectors to the plane. Okay, so a plane is basically this flat thing in space, and it has infinitely amounts of parallel vectors to this plane. As you can see, I could keep drawing vectors here and here and there and there and there. And it also has a vector that is perpendicular to all the vectors to that plane, or orthogonal to the vectors on that plane. And so just that principle helps us to do a lot. So first, it helps us. So what can we do with this is we could find that orthogonal vector by just taking the cross product of two parallel vectors on the same plane. So if I had a vector here and a vector here, I just take the cross product and I'd get this orthogonal vector. It can help us to find a distance to a point from a plane by a projection. So that's an important thing. We're going to talk about that at the end. I'll explain that more in depth. You can create a plane, and that has the equation that you need 3 points. And so if it's given you, say, like 2 points or two equations, two equations, you could set up a system of equations and solve for the plane. And if it gave you 3 points, then you could find the equation for that plane by turning it by subtracting and finding the vectors in between all three of those points. And then you cross the vectors in between those 3 points. And what that does is it gives you a normal to those 3 points, those two vectors on those 3 points, and then you can plug that into the plane equation. Then it can also help you find if two lines are on the same plane or not. So if two lines are on the same plane, then you can use a system of equations with their parametric form. So you have to turn the lines into vector form, and then from that you can find their parametric forms, and then solve for system equations. Both lines would have a different variable, and then if those equations are true, then they're on the same line, on the same plane. So basically, if two lines intersect, they're on the same plane. And so you solve for, like, if you were solving for intersecting lines. Okay, we talked about that one, and that one at the top. Okay, so we're going to talk about how to find a distance to a point that is not on the plane from the plane, and we're going to do it by projection. The book gives a formula that looks similar to the Pythagorean theorem or distance formula for if you were to find a point to a point, and so it does it for a plane. But we're going to do it with a projection, is what the professor talked about. So, example, let's just take this plane. I'm just going to talk about it conceptually. Take this plane, and there's a point in space. We can find some random point on the plane. We find that by just plugging in what works into the equation that we're given for the plane. And so we find some random point, and then we can find a vector from that point onto the plane to the point in space, but that isn't necessarily the distance. We want to find the shortest distance. And so what we want the perpendicular vector from the plane to the point out in space. So we want the orthogonal vector from the plane out to a space. So since we have a vector from a random point on the plane to a point in space, what we want to do is a projection. So what that looks like is when we have a projection, we have some vector projected onto another vector. And so in this case, we're going to do the projection of the vector from this point to the point out in space onto the plane, and it's going to equal another vector. So what that does is it takes this vector and it like kind of casts its shadow on here. And so we have now this vector shadow on the plane in a vector. So that's important. That's it. It's in a vector. So now what it's given us, it's given it this little triangle. It's given this vector here and this vector here. So this vector plus this vector is going to equal this vector. And so we know just by the projection proof that if we call this vector A and this vector B and this vector C, or yeah, the projection vector B, then A equals B plus C, but we're looking for C, so A minus B equals C. And now we have the vector that is perpendicular to the plane, and we can find that it is perpendicular by doing the projection proof from day one in class, and that this is the perpendicular vector to that point and the shortest distance from the plane to the point. Okay, that was planes real quick. Post any questions.